Good evening. Am I audible?
Yes, ma'am.
Yes, ma'am. You're
Yes,
audible.
ma'am, you are audible.
Good evening, ma'am.
everyone. So today what we are going to do is we are going to review and revise the following. That is, we are going to just go back and understand what is a random variable. We look at a few discrete distributions, namely the binomial, Bernoulli binomial hypergeometric, the Poisson, and among continuous distributions, we'll look at uniform and exponential. We'll also look at the examples of a non-uniform and a triangular distribution. So this is what we are planning for the next 2 hours. And at any point of time, you have a query, you can use the chat box. The chat box is available to me. So just to recall why we need all these distributions is I will just go back and recall what we meant by a sample space. A sample space was the set of all outcomes of a random experiment. So if you all recall, when I tossed a coin, I had 2 outcomes. The outcomes were head and tail. When I tossed a coin twice, the outcomes were head, 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 tail, tail, head, and tail, tail. Now, many a time I might not be interested in knowing as to what the outcome is, but I want to know whether I can actually give or map each of these outcomes to a number. What do I mean by that? I mean by that is it possible for me to map this outcome to a number, this outcome to a number? I'm not interested in the outcome per se, but I'm interested in a function of this outcome. So what that means is, suppose I'm interested in knowing the number of heads. You can see that I can give the number 2 here, the number 1 here, the number 1 here, the number 0 here. So every outcome is actually mapped to a number. Now this mapping of every outcome to a real number is what we call a random variable. So we are not interested in the actual experimental outcome, but we are interested in some value of a numerical value outcome. And these values, that is these real valued function defined on the sample space, are what we call the random variable. So once I have the random variable, so let's go back to this rolling a dice. I know that this is my sample space. So now I'm not interested in each of these outcomes, but if I'm interested in the outcome that of how many outcomes will result in a sum of 7. So the quantity of my interest is the sum of the outcomes. So associated with this outcome, I know the sum is going to be a 2, this is going to be a 3, this is going to be a 4, this is going to be a 5, this is going to be a 6, this is going to be a 7, so forth. This outcome is going to give me a sum of 12. So you can see that the quantity of interest here is the sum of the outcomes. So every outcome I can map to a number or a numerical value. Similarly, if I'm interested in the smaller of the outcomes, you can see that the smaller of the outcome for this outcome is a 1. Here again it's a 1. Here it's a 1. Here it's a 2. If both the outcomes are same, I'm going to take it as same. So here it is a 3. Here it's again a 3. Here it is a 5. Here it's a 5. Here it's a 5. Here it's a 4. So you can see that on the same sample space, I have defined 2 random variables. So in other words, you can see that associated with every outcome, I have a value of x. X is the sum of the outcomes. Y is the lesser of the outcome. So associated with every outcome of the sample space, we have a value, the random variable x and y takes. So far, so good. Is this clear?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
So once I know that this is the value the random variable takes, I also go back. I know that, no, it is not necessary to create a sample space all the time. Once you know the distribution, and that's where we are going to focus on today's classes, given the nature of the experiment or application, you can decide as to whether that random variable follows a distribution. But you need to understand the concept of a random variable. You don't have to write the sample space all the time. The reason why we are introducing it from the sample spaces, now I know what is the probability of this outcome 1, 1. The probability of this outcome 1, 1 is 1 by 36. The probability of each of these outcomes is 1 by 36. So given the probability of the outcomes, I can define what is the probability of the random variable taking a value. And what are the values X can take? X can take any value between 2 and 12. The values Y can take a 1, 2, 3, 4, 5, and 6. So you can see that the probability X takes the value 2 occurs only with this outcome, which is 1 by 36. Whereas X takes the value 3 happens with this, and that's it. Okay, X takes the value 3 with the probability 2 by 36. Now, if you look at X taking the value 7, you can see that it happens with 1, 2, 3, 4, 5, and 6. So probability X taking the value 7 happens with probability 6 by 36. Okay. So now if you look at Y takes the value 1, 2, 3, 4, 5, and 6. The probability with which it takes the value 6 is just 1 by 36. The probability with which it takes the value 5 is this 1, 2, 3, no other values. So you can see that I can map each of the values and find out what is the probability. For X equal to 2 to 12 and Y takes the value 1 to 36, I get what are the relevant events and what is the probability. Okay. The random variable need not always be a numerical output. The reason why we have defined it as it should be a numerical output in the sense that you are able to map the random variable to some real number. Okay. You can always say, now when you are defining that the first die is an even number, then afterwards you are assigning some value to it. So I am saying X takes some value. For example, I can say X takes the value 0 if the first die is an even, and X takes the value 1 if the first die is not even. Because there are only two possible outcomes, and that's what we will see when we are discussing binomial random variables. How are we mapping this value to a numerical value? It is important. I might not be able to physically, for example, when I'm talking about less than, it is easy for me to tell here. But suppose I'm saying that the first, for example, if you go back here, and if I look at only head and tail, I'm just assigning a value of head. If it is a head, I'm telling it takes the value 1. If it's a tail, it takes the value 0. Okay. So there is no numerical output here. Do you get the point, Arnav?
Yes, ma'am.
Output here.
Yes,
but what I'm trying to say is I'm just assigning a numerical value. Is that clear?
Yes, ma'am.
Right. So I'm assigning a numerical value. There is no numerical output in this case. So whenever you're talking about first die being an even, I can say that, okay, all these outcomes where I have a first die, it is an even, it would give me a value. The reason why we need random variables instead of individual probability is, now it is easier for me to define the values this random variable would take. I'm assigning a quantity or a numerical measure. As I said earlier, I'm not interested only in the outcomes. If you look at the first point here, I'm not interested in all the details, but I'm interested in some numerical quantity. And this numerical quantity I'm defining as a function which is mapping every outcome to this numerical quantity. That's why I'm interested in a random variable. Is this clear, the concept of a random variable?
Yes, ma'am.
Yes, ma'am.
Right. So this is the main conceptual understanding of a random variable. Again, you can see that I have, when I talk about random variables, again, I have two major categories. One is a discrete random variable and one is a continuous random variable. Just as you go back, we said that when we talk about experiments, when I had tossing a coin, I had the outcome to be a head and tail. Whether when I was asking about the time taken to reach from a point A to point B or the lifetime of a bulb, is that a random experiment when the outcome is a lifetime of a bulb? How did I specify my sample space in that case? I specified my sample space to be 0 is less than or equal to t is less than or equal to infinity. This was how it was on an interval I specified. I hope you all remember, right?
Yes.
Okay. So suppose I have, you can see that I have a sample space. And for example, when I was noting down the outcomes till I get a first head, I saw that the outcomes were a tail, a head tail, a tail head, a tail head. This is how I was telling. So you can see that the sample space need not be a finite, it could be a countable set with infinite number of outcomes, or it could be a continuous set also. Okay, so when I'm having this real valued function, I'm defining the random variable for any kind of a sample space. So this real valued function can take countable values, then I call it a discrete random variable. When it is mapped onto an interval, that is the outcomes are numerical, but it cannot be counted, I call it a continuous random variable. So discrete is a count, continuous is a measure. As rightly pointed out, a discrete is a count, continuous is a measure. So you can see that a discrete random variable will typically involve counting, and continuous random variable typically involves measuring. So from an application point of view, whenever, for example, when you're talking about height or weight, you don't count height or weight, you measure it. Rather, when you are counting the number of successes or number of failures or number of accidents, this involves counting. You model it as a discrete random variable. So far, so good? Yeah.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
This understanding, we will look at what are the situations which can be modeled as discrete. So as I said, whenever you're counting, that could be number of people, number of languages, or number of times a person takes a particular test. I'm saying number of times a person takes a particular test. I'm not saying that time taken by a person to write an exam. When I'm measuring the time taken by a person to write an exam, it would be a continuous variable. Whereas when I'm looking at the number of times a person takes a particular test before qualifying, that would be a discrete random variable. Okay. So number of spelling mistakes, whereas when I'm measuring the temperature of a person or a height of a person or a speed of a vehicle, you can see that these are all measured and they could come as, or they could be modeled as continuous random variables. So for the rest of the session, we are going to focus on specific distributions which are modeled as a discrete or continuous. So we are going to look at some special distributions or very well-known distributions. When I'm looking at discrete, what we are going to look at is, we are going to look at Bernoulli, binomial, and all those random variables. When I'm looking at, so for discrete, I'll look at Bernoulli, binomial, hypergeometric, and Poisson. And for continuous, we look at uniform, exponential, with giving examples about non-uniform distribution. But before I go and look at these specific distributions, let's introduce a notion of a probability mass function and a probability density function. Now, when I said that a discrete random variable will take at most countable number of possible values. In other words, what we mean by that is x takes some values x1, x2, x3, and this x1, x2, x3 are on the real line. So associated with every x taking a value x1, x2, x3. For example, when I'm counting the number of heads, when I toss a coin twice and I count the number of heads, I have a HH, HT, and HH. X takes the value 0, 1, 2. Associated with every value x takes, I know what is the probability of x equal to 0. Probability of x equal to 0 corresponds to the outcome PT. So the probability of x equal to 0 is 1 by 4. Probability x equal to 1 corresponds to these two outcomes. So that is going to be a 2 by 4. And probability x equal to 2 corresponds to this outcome, which is going to be a x equal to 2 is again 1 by 4. So corresponding to every outcome, I can see that I have a probability associated with it. And that probability x equal to xi is what we refer to as the probability mass function. So you can see that when I have what are the key properties of the probability mass function? This, since this is a probability, this should be greater or equal to 0. Okay. And the summation of all probability has to be equal to 1. So one of the questions definitely that you might have seen in your assignments and everything is to verify whether a given function is a probability mass function. So when you get questions of the kind where you are asked to verify whether a function is a probability mass function or anything, the two things you need to verify is whether each one of them is greater or equal to 0 and whether they collectively or exhaustively they add up to 1. For example, I could have a minus 1 by 2, 3 by 4, and 1 by 2. And sorry, minus 1 by 2, 1 by 4, and I could have a 3 by 1 by 2, and I could have a 3 by 4. Now these add up to 1, but this is not greater or equal to 0. So this is not a probability mass function. If I have a 1 by 2, 1 by 4, 1 by 4, 1 by 4, this also does not add up to 1, even though all of them are greater or equal to 0. So the first thing that you need to check is whether the probabilities are greater or equal to 0 and whether they add up to 1. This is when you can verify whether any given thing is a probability mass function or not. The next thing is the shape of the distribution. We can plot the probability mass function by on the x-axis we have the values this random variable takes. For example, in this case, x takes the value 1, 2, 3, 4. And the probability, now this is a probability mass function because each one of these probabilities are greater or equal to 0 and they add up to 1. 0.4 plus 0.3 is 0.7, 0.7 plus 0.2 is 0.9, 0.9 plus 0.1 is 1. So they add up to 1. So given this, I can plot this distribution. What do I mean by plotting this distribution? I write the values this x takes on the x-axis. X takes value 1, 2, 3, and 4. The probability with which x takes the value 1 is 0.4. So I have a bar which is at 0.4, a bar which is at 0.3. This is equal to 0.3. This is equal to 0.2. And this is equal to 0.1. Now, what is the use of this graph of the probability mass function? It in a way tells us whether the random variable is symmetric or is it skewed, or it somehow tells us the shape of the distribution. For example, I could have a positive skewed distribution, I could have a negative skewed distribution, or I could have something which is symmetric also. When it is symmetric, I could have a 0.1, 0.2, 0.2, and a 0.2, 0.3, 0.3, 0.2. So this would be symmetric distribution where this is a 0.3, 0.3, 0.2, 0.2. That would be symmetric. So in a sense, the graph skewed. What is skewed is if it is bent to one side. For example, if you look at this graph, you can see that the values, this is not symmetric. So if you look at the shape of a distribution, this would be a symmetric distribution. So when I look at shape of a distribution, I'm having x here. I have probability x equal to x. It is sort of the probability, this shape is not symmetric. This shape is symmetric. Okay. This shape is again not symmetric. The relevance of calling it as a positive skewed or a negative skewed is basically whether it's left skewed or right skewed, whether the probability. So when you are looking at it is not, so the values are actually skewed to one side. You learn more about skewness when you are actually, why is skewness important is, again, you can look at skewness because skewness and symmetry, the shape of a distribution plays a big role when you are trying to look into applications. Okay. Yeah, the type of inference at this point, you really do not have any type of inference by the skewedness. But if you have a skewed distribution, then afterwards it all depends on whether you can actually approximate it by a known distribution or not. You'll be learning all of this in your statistic 2 course. At this point of time, just remember symmetry. Skewness is to one side. It could be left skewed or right skewed, which is other. In other words, it could be positive skewed or negative skewed. At this point of time, please remember that. And from what gives us an indication of the shape of the distribution? An indication of the shape of the distribution is given by the probability mass function. So today this will become clearer to us when we look at specific distributions, and we will be talking about that in quite some time. Now, when I talk about a continuous random variable, I do not have in a continuous random variable x taking points x1, x2, x3, x4. Rather, I have that x belongs to an interval. So I do not have these bars anymore. I have these bars are approximated by a curve, and I can say that this f of x is a probability density function. The equivalence of probability of x is greater or equal to 0 is f of x is greater or equal to 0. And the equivalence of probability xi over all values is equal to 1 is same as over this interval. Say this interval is a to b, f of x dx, the area under the curve. We all know that the definite integral a to b of this curve, where this curve is my f of x curve, this should be equal to 1. So when I'm looking at a discrete, I know that I have points. When I have a continuous random variable, I have an interval. And the area that the probability x belongs to this interval is a to b f of x dx. And I know that the area under the shaded area under the total curve should be equal to 1. So these are the first two important notions. When I have a discrete random variable, I have the notion of a probability mass function. When I have a continuous random variable, I have the notion of a probability density function. The next important notion is that of a cumulative distribution function. Now, when I have a cumulative distribution function, what it means is I am mapping every value on the real line. So the way I define f of a is probability x is less than or equal to a. In probability mass function, you have summation probability x equal to xi over all values xi takes equal to 1. This is the same as over whatever interval you have defined your probability density f of x equal to 1. Okay, that is what it means. This is an area under the curve should always be equal to 1. Okay. That is the distribution, because I am exhausting everything, because the way I have defined a probability mass function is f of x takes some value. If a is less than or equal to x is, suppose this is an a and this is a b, it is 0 otherwise. So I know that the area under the curve is 1, which is same as a to b f of x dx should be equal to 1. Integral does not take continuous value. F of x is defined to be this curve, which is continuous. Okay. The way I define this is x, probability of x belonging to an interval is a to b f of x dx. That's how I'm defining. For a continuous random variable, I do not define probability x takes a particular value. Okay. It is this function for which I have area under curve. I do not define a probability x equal to a value. If you see that I define that the probability x assumes a value between a and b in a continuous distribution. You can see that probability x equal to a particular value in a continuous distribution is actually, you do not define that. You just define probability x belongs to an interval. Is that clear?
Yes, ma'am.
Yeah. Okay, so now,
Yes, ma'am.
next important thing is the concept of a cumulative distribution function. So when I define a random variable, the first two things I did was I first decided what is a continuous random variable, what is a discrete random variable. For discrete random variable, I had what I call a probability mass function. For continuous random variable, I have what is a probability density function. And remember, both the random variables, be it discrete or continuous, are mappings of your outcomes in the sample space onto real numbers. Either it is countable or it is in a set. So the next thing is the cumulative distribution function. Now, as the name suggests, what is cumulative? Cumulative says that I know, for example, x suppose takes the value 0, 1, and 2. I know that if 0 is less than x is 1 is less than 2, that is where x1 is less than x2 is less than x3, then I might be interested in knowing what is probability x is less than or equal to 1. Now, why are we even interested in such a thing? For example, now you look at this where I have x is taking the value 1, 2, 3, and 4. I know 1 is less than 2, is less than 3, is less than 4. And I've been given that x takes the value 1 with probability 1 by 4, 2 with probability 1 by 2, 3, and 4 with probabilities 1 by 8 each. I can verify this is a probability mass function because 1 by 4 plus 1 by 2 plus 1 by 8 plus 1 by 8 is equal to 1. So this is a probability mass function. Okay. Now the next thing is, I want to now, suppose this is the number of people who have, for example, I'm looking at x taking a value and I know that x, this is the number of people in who have got, for example, 1 job or 2 jobs or 3 jobs, number of jobs a person has got in a class. Okay, suppose I'm looking at that distribution. And if I'm asking the question, how many people have got at most 2 jobs? Okay, I'm saying that in a class, I know that this is the probability that a person would get exactly 1 job is 1 by 4, has got 2 jobs is 1 by 2, 3 jobs is 1 by 8, and 4 jobs is 1 by 8. Suppose I'm asking the question, what is the probability that a person gets at most 2 jobs? Now, what is at most 2? How does that translate in terms of x? X is less than or equal to 2, is what I want to know. Right?
Yes, ma'am.
At least 2 would be x
Yes, ma'am.
greater or equal to 2. So I'm interested in knowing this probability. I know probability x equal to 2 is 1 by 2. But now I'm interested in knowing what is probability x is less than or equal to 2. So when I want to know what probability x is less than or equal to 2, it is probability x equal to 1 plus x equal to 2. So I'm accumulating these two probabilities, that x equal to 1 and x equal to 2. So I know that if I want to know probability x is greater or equal to 2, I know it is probability x equal to 3 and x equal to 4. So I define what is called a cumulative distribution function. And a cumulative distribution function If A is less than 1, I do not have the probabilities defined. So that would take the value 0. For 1 is less than or equal to A is less than 2, it will take the value 1. So I know that I can plot it in this way. Till A takes the value 1, it is going to remain 0. At A equal to 1, it takes 1 by 4. It remains at 1 by 4 till it heads 2. Once it hits 2, it is going to be 1 by 4 plus 1 by 2, which will be 3 by 4. It is 3 by 4 till it hits 3. Then it takes the value 7 by 8. Then it takes the value, after this one, it takes the value 1 and it remains 1 after that. So this type of a function is what we refer to as a step function. You can see that these are dotted, indicating that it is not a continuous function. So the cumulative distribution function for a discrete random variable follows the step function. So you can see that it has discontinuities, and these are the discontinuities. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Probability 1.2 is 0, but f of 1.5, right? See, when you're saying probability f of 1.5, f of 1.5 is probability x is less than or equal to 1.5, which would be probability x equal to 1. Okay, so where does 1.5 lie? 1.5 lies here, right? So you can see that this is the probability of 1.5 would be 1.25, which is 1 by 4. See what I'm saying. See, the use of CDF is to answer, see, probability mass function or probability density function. Probability mass function, first of all, is for a discrete random variable. Probability density function is for a continuous random variable. Now, cumulative distribution function, for example, in this, again, if I go back here and tell you that X is the number of jobs offered to graduates in a passing out batch of a large university. What are the values this X can take?
Discrete.
It is taking, because I'm saying number of jobs, it is taking values 1, 2, 3, and 4. Okay. Now, what is the use? If I were to ask the question, what is the probability that any person or would have exactly 2 jobs, then I would use a probability mass function to answer that question. Would you agree?
Yes, ma'am. Yes.
If I'm interested in
Yes,
knowing
ma'am.
the probability that a person gets at most 2 jobs, or what is the probability of people getting at most 2 jobs, it is probability X is less than or equal to 2. So I'm using the concept of a cumulative distribution here. I'm accumulating it. Is that clear?
Yes,
Now,
ma'am.
when I have a discrete distribution, I have these points of discontinuity, because if you have learned about limits from your mathematics thing, you can see that as I am going, this f of x is, as I'm reaching 1, okay, till it is 1, it is 0. At x equal to 1, it is taking the value 1 by 4, right? So the right limit and the left limit are not the same here. So this is a point of discontinuity. Would you all agree? So that's why it is a dotted line.
Yes,
Similarly,
ma'am.
there are points of discontinuity here. So this function is not a continuous function. Is it clear? This would follow a step function. It is a non-decreasing, it is increasing, but it's a step function. This is for a discrete random variable. Whereas, we'll look for a continuous random variable in some time. Okay, but this is clear. For a discrete random variable, it is this way.
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
It would be cumulative distribution only. It is whether it, see, probability density, because I'm talking about area under a curve, mass because these are bars. That is the understanding which you should have. Okay. At x equal to 3, probability of x equal to 3 is 1 by 8. Probability x is less than or equal to 3 is 7 by 8. Is it clear? That's a difference. Probability x equal to 3 is 1 by 8. Probability of x is, so probability x equal to 3 is 1 by 8, but f of 3 is 7 by 8. Okay. So now, just as we define what is this one, we have what is an expectation of a random variable. We'll talk about the CDF even of, okay, let's go and talk about a CDF of a continuous random variable and come back here. When I have a continuous random variable, for example, if I'm defining, let me go back to this continuous random variable, 1 second, yeah. Okay, so suppose I have a continuous random variable here, okay. So what does that mean in a continuous random variable? I have some sort of a curve. I am defining, say, let me take any 2 points A to B. Okay. I know that this is this function f of x, and I know that this f of x A to B, the area under the curve is f of x A to B. This is equal to 1. Is that clear?
Yes, ma'am.
Yes, ma'am.
So suppose
Yes,
I am
ma'am.
interested in knowing, suppose this is the heights of people in a particular class is distributed between A and B. So suppose I'm saying the heights of students in any particular class is distributed with some value. Okay, I'm telling f of x with this density, where this f of x is this curve. Okay. Say I'm telling that the heights are distributed according to this curve between A and B. A is the least height and B is the maximum height. Okay. Now suppose I want to know the number of people who have height less than or equal to C. What does this mean? In terms of, so x is the heights of people. I'm saying the heights of people follows this distribution given by f of x. Okay. And I know the area under this curve is this one. Now I am interested in knowing what is the height of people less than or equal to C. That would be equal to A to C f of x dx. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Yes.
Right. So that is what a cumulative distribution function will tell us. What is the chance of, and this could be heights, it could be even temperatures of people between A to B, or it could be weights of people between A to B. Whatever it is, in a continuous scale it is. So I am interested in knowing what is the probability of finding x is less than or equal to C. And that would be this area. Is this clear?
So, ma'am,
Yes, ma'am.
Yes, ma'am.
in continuous random variable, we talk only about CDF, is it?
You talk about PDF. CDF is there both for continuous random variable and discrete random variable.
But whenever we answer the questions, we use the CDF formula, right?
See,
Because P of x less than.
Let me clarify this. See, I have a discrete random variable. I have a continuous. Let me go to the whiteboard. Just give me a minute. Okay. I think there should be a whiteboard here. Are you able to see the whiteboard?
Yes, ma'am.
Yes, ma'am.
Okay. So what we have done so far is,
Ma'am, in that case, can we take as probability of C minus probability of A divided by 2?
1 second. Let me start this and then we'll look at it. Okay. Well, you'll agree this is discrete, this is continuous random variable.
Yes, ma'am.
Right. So in discrete random variable, I say that x takes values x1, x2, x3. If it is finite, it will take x1, x2, x3. All of this is countable if it is infinite. Okay. Now an example for this finite is I toss a coin. I note the number of heads, HH, HT, TH, and TT. What are the values x is taking in this case? Counting the number of heads. It is taking the value 0, 1, and 2, right? Now, suppose I am doing an experiment and I'm counting the number of toss in which I'm getting the first head. First, it could be in my first toss. It could be in my second toss. It could be in my third toss. Okay. So what are the values x is taking here?
1.
1.
1.
Or it could be in okay. 0. Okay, let me say it could be in the first 1, 2, 3. It is continuous. So this is associated with this, and here it is countable, but it is infinite number of values. So far, so good.
Okay, ma'am.
Is this clear?
Yes.
Right. Now associated with every x. So now, so I am just going to use this notation here because I know that if x takes values x1, x2, x3, so forth, associated with everything, I can define a probability x equal to x1, x equal to x2, so forth. I can do that. One second. Probability x equal to x3. I can do this. Would you all agree?
Yes, ma'am.
Yes,
Now,
ma'am.
this is what I refer to as my probability mass function.
Yes.
Okay. Right.
Okay.
PMF, probability mass function.
PMF.
You can call it a PDF also, but you should understand it that I don't have a density here. I have a density is usually when you are talking about on an interval, right?
Okay.
Whereas this is probability x equal to something. It's some sort of a mass. Is that clear?
Yes, ma'am.
Now the same thing when I'm looking at, say, heights of people, I don't say that x is equal to something. I say x is between 20 between the 20 heights of people. I can say, okay, x is between 75 centimeters to 80 centimeters, 80 centimeters to 85 centimeters. This is how I'll define it. Is that right?
Yes, ma'am.
So instead of getting a probability x equal to something, I am telling that this is what I'm going to call a function. So I define it as a probability f of x, where this f of x is a to b, that is a probability x belongs to a to b. Okay, one second. Okay, where I am writing probability x belongs to an interval is a to b f of x dx. In other words, I have an a, I have a b, and probability x belongs to this integral is the area under this curve. So far, so good?
Yes, ma'am.
So continuous and discrete, this is what I call the PDF. In continuous, I have the PMF. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yeah. Okay. One second. Let me. Okay. What happened to the whiteboard? Okay. Right. So now. Okay. So now let me clear this. Okay. So now is the PMF and PDF clear? PMF is what I'm going to use for. So here I have x taking value x1, x2, x3. Here I have x belonging to any interval a to b. Okay. Now I'm interested in knowing, I want to know what is the chance that x is less than or equal to some p. Okay, p is some real number. Okay. Now, if that p is here, what is that chance that x is less than or equal to p? If p is here in this case.
The sum of the probabilities of x1 and x2.
Probability x is equal to x1 plus probability
Yes,
x is equal to x2. Is it right?
Yes, ma'am.
Yes,
Now,
ma'am.
if p is here, suppose x1 is less than x2 is less than 3. If p is here less than x1, what would be a probability x is less than or equal to? It would be
0.
b. Now, suppose p is here greater than x3, what would be probability x is less than?
0.
0.
Will it be, no, if p is here,
Ma'am, 1.
it will be 1, right?
1, 1. Yeah.
Is it clear? Okay.
Yes, ma'am.
Yes,
Now,
ma'am.
similarly, if p is outside the interval here, what would be probability x is less than or equal to p?
0.
0.
P is greater than b, then what would be probability x is less than or equal to
1.
If p is here, it would be a to c f of x dx. Is it clear?
Yes,
Yes,
ma'am.
Yes, ma'am.
This is the notion of the cumulative distribution function. Is this clear?
Yes.
Yes, ma'am.
Thank you.
Okay, right.
Yes, ma'am. Thank you.
Okay, right. So now, is the PDF visible? The PDF visible?
No, ma'am.
Yes, ma'am.
Yes,
Now
ma'am.
Yes,
Now
ma'am.
it's visible.
Yes, ma'am. Now it's visible.
Right. So now I'm just going to skip over this expectation. I just tell you what is the definition of expectation. So the expectation is xi into probability x equal to xi, and variance is xi square, expectation of x minus mu whole square. We will compute the probability of n into expectation of, what is that pi? I'm not sure what is pi. I do not know what is pi. So we'll have a look at it later. Okay, it is x minus mu probability of xi. But once you're taking expectation of x whole square, yeah, it would, that is expectation of x whole square, right? That would be fine. But this is a computational formula. You can check that that would be the same. Okay, right? It would come to be the same, whatever you're using. But so now what we are going to do is to understand certain discrete distributions. Okay. Any questions still here? We will compute the expectation and variance for all the random variables.
No, ma'am.
Okay. The first basic is, again, when I look at any experiment wherein I have only two outcomes, I call one outcome a success and one outcome a failure. Okay. Now, what all can be modeled at it? For example, if I toss a coin, how many outcomes do I have?
two.
Outcomes.
Two.
Okay, I can call one of them to be a success, head is a success, tail is a failure, or tail is a success, head is a failure. Okay, now if I roll a die, okay, and I am also going to count, if it is even, I call it a success, if it is odd, I call it a failure. I can do that?
Yes.
Yes, ma'am.
Yes, ma'am.
I can, so in all the experiments where I can have these two outcomes, I call it a Bernoulli experiment. So I am just telling that X takes these two values. So it takes a value 0 and 1 with probability P. If it is taking the value 1 with probability P, it should take the value 0 with probability 1 minus P. So far, so good?
Yes, ma'am.
Yes, ma'am.
Yes.
So now the expectation of this X is going to be 0 into 1 minus P plus 1 into P, which is just going to be P. Okay. Now variance of this binomial, this one is, again, you can verify what would be the variance of this. This is going to be expectation of x square. What is expectation of x square? Expectation of x square is again 0 into 1 minus P plus 1 into P. So it is P. So variance of X is going to be expectation of X square minus expectation of X whole square. This is my computational formula. You can see that variance of X is expectation of X square minus expectation of X whole square. In a binomial case, expectation of X square is P. In a Bernoulli case, expectation of X is also P. So I get P minus P square. And the variance of a Bernoulli random variable is P into 1 minus P. So if I have to plot this PMF, I know that X takes the value 0 and 1. This is taking the value 1 minus P. This is P. Now, if P and 1, if P is half, then I'll get this way. If the probability of success is more than probability of failure, I get it this way. If the probability of failure is more than probability of success, I get it this way. So this is how you can understand what is the expectation of this random variable and variance of this random variable. Now, suppose I'm having, for example, I toss a roll a die. What are the possible outcomes of that die? I roll a die.
6 faces.
1 to 6.
Okay, and X takes the value 1, 2, 3, 4, 5, 6. What is the chance of me finding a 1?
1 by 6.
1 by 6.
1 by 6, 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 1 by 6. Okay. Suppose I'm having 100 chits number 1 to 100 I have written in these chits and I put it in a ball and I ask you to randomly pick up one chit. Okay, what is the chance that you'll pick up one chit?
1 by 100.
1 by
1 by
100.
100.
1 by 100.
What is the chance that you'll pick up a chit which has 46 written on it?
Also 1 by 100.
38?
1 by 100.
100.
The probability, so this n, given any n, I know that the chance of me picking up any chit is going to be 1 by the number of chits in that. Now the probability mass function for such a experiment or random variable would be this way. You can see that all the heights of all the bars are the same.
Yes, ma'am.
Yes, ma'am.
This is what we refer to
ma'am.
as a discrete uniform random variable. Okay. Now, where would we use it? Suppose in a class I have that so x is taking the same value 1, 2, 3, 4, 5, 6, rolling a die. You can see that this is taking the same value here. Now, what is the expectation of this random variable? It will be 1 into 1 by n plus 2 into 1 by n plus n into 1 by n. So it is 1 plus 2 plus n into 1 by n. What is 1 plus 2 plus 2 plus 1 by n? It is n into n by 2, n plus 1 by 2. So I'll get expectation of this random variable is n plus 1 by 2. Okay, expectation is a long run average. Why do we say it is a mean value? Very rarely do we say expectation is a mean value, because mean is what is finally you expect. Okay, that's why you say a long run average. That's why you are saying it's a mean value. Okay.
Yes, ma'am.
Okay, see, expectation, again, you need to understand expectation is in the world of uncertainty. Expectation is in the world of uncertainty. So I am expecting something to be in this one. So it is, yeah, if you are having different weights also, it would be a weight. It is a notion of a weighted mean in a discrete random variable case. Okay, right. Now, the most important or most widely used application is what we refer to as the binomial random variable. Now, to understand what is a binomial random variable, it is very important for us to understand what is an independent and identically distributed Bernoulli trial. Now, for example, I'm tossing a coin 10 times. Okay. Now, what are the possible outcome of each trial?
Heads or tails, any of these.
Okay, so if I'm tossing a coin, so trial 1, what are the possible outcomes?
Head or tail?
Trial 2?
Head or tail.
Trial 3, trial 4, each one of them have only 2 outcomes. What is the chance of getting a head in the first outcome?
1 by 2.
1 by 2.
Chance of getting a head in the second outcome?
0.5.
1 by 2.
1 by 2, 1 by 2. So in a sense that, does the chance of you getting a head in the second outcome, does it depend on whether you had a head or tail in the first outcome?
No, ma'am.
So it is independent. You can see that I can view this 10 trials as independent, because the chance of the outcome in this, or the probability of success in my second outcome or each outcome, is independent of the probability of success of the other outcomes, and it is identical also. Identical in the sense the probability of success remains the same.
Yes,
Is it right?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Yes.
So that's why this is called an independent and identically distributed Bernoulli trial. In some time, we'll see what happens when it is non-independent and non-identically distributed. Okay. So when I have n independent trials and I know that the probability of success of each trial is P. Okay. The probability of success is P. The probability of failure is 1 minus P. Okay. So if I have n trials, okay. So let me say, for example, n is equal to 3. Okay. Now, what are the possible things in this n equal to 3? All 3 could be failures. All 3 could be successes. Or I could have 1 failure and 2 successes. I could have one success and 2 failures. What else can I have? What else could I have?
2 failures and 1 success.
That is already have. So I could have all 3 successes, 3 failures, 1 success, 2 failures, 2 success, 1 failure. Is there any other chance I could have?
No, ma'am.
These are the possible things I can have.
Yes,
Yes, ma'am.
ma'am.
Yeah, okay. So what are the values? Suppose X is counting the total number of successes. What are the values this X will take?
0, 1, 2, 3.
0, 1, 2, and 3.
This is 0, this is 1, this is 2, and this is 3.
3.
So, agreed?
Yes,
Yes,
ma'am.
ma'am.
Suppose n equal to, suppose I'm doing this 10 times. So what are the possible values X will take in that case?
0, 1, 2.
1 to 10.
0, 1 to 10. Is that clear?
Yeah.
Yeah. Okay. Now I'm interested in what is the chance of this outcome happening? That is all 3 successes. I'm tossing a coin 3 times. What is the chance of all 3 successes happening? The first is a success, second is a success, third is a success.
1 by
1 by 8.
What is the chance of no success happening? That's also 1 by 8.
1 by 8.
Okay. The chance of 1 success happening can happen this way. 1 success happens in the first toss. 1 success happens in the second toss. That success happens in the third toss, right?
Yes, ma'am.
So this chance would be 3 by 8.
3 by
This
8.
chance would be 3 by 8, right? In general, if I'm having n tosses, okay, the probability of X equal to I would be, I have I successes, I'll have n minus I failures. Is that right?
Yes,
Yes,
ma'am.
ma'am.
Right. I have I successes and n minus I failures. N minus I failures is happening with 1 minus P. I successes would be, since they are identical and independent, I can multiply them. Or remember our multiplication rule. Is that clear?
Yes, ma'am.
Now,
Yes, ma'am.
these I successes, this can happen in, again, how many outcomes do I have? N. What is the permutation, or how many ways can I successes be arranged in n total outcomes? I have only success and
N ways.
failure. How many ways can I successes? N choose I.
And
Right?
CI.
And choose.
So the probability of X equal to I is nothing but N choose I, probability P equal to I, and 1 minus P, N minus I. Is this clear?
Yes, ma'am.
Yes, ma'am.
This is what we call
Yes.
as the probability mass function of a binomial distribution. Okay. Now, once I know the probability mass function, I can find out the most important thing which I need to know is, once this P is equal to half, I get what is called a, so when P equal to half, you see I have symmetric distribution. Is that clear?
Yes, ma'am.
P is less than
Yes,
half.
ma'am.
This is a right skewed. So now you can see that when P is less than half, I have a right skewed. When P is greater than half, with P equal to 0.8, I have a left skewed distribution. This is what we have seen already. Yeah.
Yes, ma'am.
Again, I'm saying you the notion of skewness you'll get to know about the notion of skewness very quickly. Now, what I want you to see here is when n equal to 4 and P equal to 0.5, it is symmetric. I just keep increasing this n. Okay. N equal to 40 and P equal to 0.3. What do you notice as the shape of the distribution? When n equal to 4 and P equal to 0.3, I had this as the shape. Okay. I'm keeping P is fixed, but n equal to 40. What is happening to the shape? It's becoming symmetric.
It is
When n
tending
equal to 40 and
to
P equal to
be
0.3,
symmetric.
it is becoming symmetric. N equal to 40, P equal to 0.5, also it's becoming symmetric.
Yes, ma'am.
Right?
Yes, ma'am.
Yeah.
Yes,
Do we use binomial distribution? PMF is there for every discrete distribution. There is not that we're using binomial over PMF. Okay. This is the probability mass function of a binomial distribution. This is the PMF of a probability the binomial distribution. Where do you use a binomial distribution? The conditions where you use a binomial distribution is, for example, if I know that, for example, in a shop, if there are two outcomes, a person buys or does not buy. Okay, I have customers entering a shop and the possible outcomes are buy and do not buy. I have 100 customers visiting a shop on any particular day. What is the chance? Suppose a customer buys with a probability of half and does not buy with a probability of half. I want to know what is the chance that, what is the probability that 50 people made a purchase. Is this a binomial distribution? I have 100 customers visiting a store. I want to, and there are two possible things. Any customer can buy or do not buy. Okay.
Yes, ma'am, it is binomial. Because
It's
there are
binomial. The
Binomial.
chance that a customer buys or customer A buys or does not buy is independent of customer B buying or not buying, right?
Yes, ma'am.
Yes.
And I'm assuming that they're equal chances. And I want to know what is the probability that 50 people made a purchase or something, then I can use it as a binomial distribution.
Yes, ma'am.
Okay.
Yes, ma'am.
Right. Binomial distribution has a probability mass function. You need, these are well-known distributions. Okay. It is not that binomial, you are using binomial over PMF or anything of that kind. You need to identify whether I can model it as a binomial distribution or not. I hope it is clear.
yes, ma'am.
Yes, ma'am.
Right. So what you notice is, as I keep increasing n, for the same p, I get a different distribution which looks to be symmetric. Now, this is what you would learn in your statistics too, when you have to get into what is called the central limit theorem. I'm not going to there, but I want you to recall this concept when you will be introduced to that. Okay. Now, the expectation and variance of a binomial random variable. Expectation is nothing but n into p. The variance is np into 1 minus p. I'm not going to derive that here. You can, that is, if x is a binomial distribution with parameters n and p, these are called the parameters of the distribution. So I specify what is n and p. I know that expectation of x is n into p and variance of x is n p into 1 minus p. The derivation you can refer to the lectures. I have derived that in the lectures. Is this clear till here?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Now, the next important thing is how graph changes when we vary p. Yeah, it will change now, because when you vary p, this changes, right? P to the I and 1 minus p to the n minus I. If it is 0.5, it is just 0.5 to the power of I. Otherwise, if it is 0.25, it would be 0.25 to the power of I and 0.75 to the power of n minus I. So your graph would change. When you vary p, the probabilities would change. Okay. You can try that out. For n equal to 4 and p equal to 0.5, you can just try it out. It's very simple. You can calculate the probabilities and you can see that the graph changes. Okay. Now suppose, let me, so when we saw this head and tail, you saw that the first toss is a head and tail. I'm assuming equal probability. When I'm tossing it for the second time, the first toss is a head and tail. The second could be a head and tail. First toss is a tail. The second could be a head and tail. I said these are independent and identically distributed because this is having a probability half, half. Here, this is a half. This is also a half. This is a half. This is a half. This is a half. This probability would be 1 by 4. This would be 1 by 4. This is 1 by 4. This is 1 by 4. Right? This is what we saw. Now let's look at this experiment. I have a ball, a bag with 4 white balls and 3 black balls. Okay. What is the chance of me picking up a black ball?
3 by 7.
3 by
3
7.
by 7.
What is the chance by which I pick up a white ball?
4 by 7.
4 by 7.
Okay. Now I'm not replacing the ball. So if I pick up a black ball, how many balls have I left?
2
Take
black.
2.
6 balls.
I'll have 4 balls and 2 black balls.
Yes,
Yes.
Here
ma'am.
I'll have 3 white and 3 black.
Yes, ma'am.
Yes, ma'am.
Now what is the chance of me picking up a black ball?
2 by 6.
2 by 6 plus 3 by 6.
What is the chance? So is the chance of me picking up a black ball in the second trial the same as the chance of picking up a black ball in the first trial?
No, ma'am.
No.
So is the first and second trial independent of each other?
No, ma'am.
No,
Ma'am.
They are identically distributed?
No, ma'am.
No, ma'am.
Here you can see that, can I model this situation as a binomial distribution if I want to know the number of black balls in 2 trials?
No, ma'am.
No, ma'am.
So do you understand the requirement of IID in a binomial distribution?
Yes,
Yes,
ma'am.
ma'am.
Okay, so this I'm losing what is the independent thing here. So for this is where we introduce what is called a hypergeometric distribution. Okay, so when I want the hypergeometric distribution to work, I need the population to be divided into 2 independent subsets. Okay, so I have, suppose I have n, which is the total. Here, how much was n? 7, right? I have divided this into m and n minus m. Okay, so how many? I had 4 black balls and 4 white balls, and 7 minus 4, 3 white balls. Is that clear?
Black ball.
Black balls, ma'am.
Black ball.
Yeah, sorry. I have black balls. I had here n equal to 7. I had 3 and I had 4. Is this clear?
Yes, ma'am.
Yes, ma'am.
Okay. Suppose I'm randomly selecting 3 items from this 7. Okay, I'm randomly selecting 3 items from this 7. Now I could have a mixture of black and white in that.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yeah, is it clear? I could have a mixture of black and white. So let me call the number of black balls in that to be small x, and number of white balls would be n minus x. Because if I'm selecting n equal to 3, right? What are the possible things that I could have? How many black and how many white? And I'm selecting 3 from this 9, right? And I'm counting the number of white balls. What is the probability of, suppose, hello? Can you mute, please? Yeah, I'm counting the number of black balls in this sample. What are the values that can take?
0,
0 to
1,
3.
2, 3.
Can take 0, 1, 2, and 3. Is that clear?
Yes, ma'am.
Now, if I'm counting the number of white balls,
Same.
4.
what are the values that can take?
0 to 3, ma'am.
0 to 3. Suppose I am choosing 4 balls here. What are the, if I'm counting the number of black balls, what is the value that this can take?
0 to 3.
0 to 3.
Again, white balls,
0 to 4.
0 to 4.
4. Is it clear? Can x take the value 0? What does it mean x takes the value 0?
There is
No
no
black
black
balls is
ball.
0, 1,
No
2,
black
3. Okay. What is the thing that white x takes the value 0 for a white ball?
No white ball.
No white ball.
If no white balls, then what does it mean?
All black
All
balls.
black
All
balls.
black
Can I
balls.
have 4 black balls?
No.
No.
What are the values it will take here? White balls?
1 to 4.
1 to 4.
It cannot take the value 0.
0. Yes.
Yes, yes.
Yeah.
Yes, ma'am. Yes.
It will. Yes, ma'am.
Huh? It cannot take the value 0, right? Because if it takes the value 0, it means that all the 4 balls should be black, but I have only 3 black balls.
We have only 3 black balls.
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Yeah. So the way I can write here is, so x takes the value 0, 1, 2, but then afterwards, what are the values? It depends on what is this, n is less than m. Okay, it depends on what is your n and m, and it will take that value. Is that clear, please?
Yes,
Yeah?
ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Now the expectation of this. So now suppose I have this, you can see that the probability x equal to I when n equal to 2 and m equal to 3 would be given by So how many ways can I choose? Suppose I have, this is my thing. How many ways can I choose small n from this? How many ways can I choose small n balls from capital N balls?
NCN.
So that would be on my denominator. How many ways can I choose x balls from m balls?
3 max.
M choose x.
MCX.
And I can choose n minus n box from n minus m. It's n minus m choose n minus x. So
N minus x.
this is the probability mass function of a hypergeometric distribution. Is this clear?
Yes, ma'am.
Yes, ma'am.
So the expectation and variance is expectation. So now if I have m of one type and n minus m of the other type, the expectation is n into m by n, and variance is n into m by n into n minus m by n. Okay. Now I just want you to look at this for a minute. Okay. That is n into m by n. I am going to write this as n into m by n. Here I'm going to write it as n into m by n. Would you all agree that I can write this as n into 1 minus m by n?
Yes, ma'am.
Can I? Yeah. And this I can write it as 1 minus n by n. 1 minus 1 by n. Can I do that?
Yes, ma'am.
Yeah. Okay. Now I want to write this as n into m by n into 1 minus m by n. Okay. Right?
No.
N minus m. Okay, this I'm writing it as and 1 minus n by n, 1 minus 1 by capital N. Now, just look at this thing. Okay. Now, what is this? I have here n. M is of one kind and n minus m is of the other kind. Okay. Right? Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now, suppose I increase this n. Okay. N equal to 20, m equal to 4. Okay. Suppose I'm increasing this m, n equal to 100 and all of that. This is the graph of the function. Is that clear? N equal to 20, m equal to 10, n equal to 10, n equal to 100. I'm increasing n and m, keeping small n the same. Keeping small n the same, I'm increasing n and m. Capital N and m. Okay, I'm keeping small n the same. What is it you're noticing? As I'm keeping small n the same, I'm keeping small n the same, I'm increasing capital N and capital M. What do you notice?
Symmetric distribution.
It's becoming symmetric and
Symmetric. Yes, ma'am.
not only symmetric, are you able to recognize this distribution in some way? Something of this kind? As I keep small n.
Normal distribution.
We are not discussed about normal. Does it look like a distribution of your binomial?
Binomial distribution. Yes, ma'am.
You just seen the binomial now?
Yes, ma'am.
Yes,
Yeah.
ma'am.
Okay. So now you can see the binomial versus hypergeometric. When I have p equal to 5, okay, what is my m by n here? M by n, small m by capital N.
1 by 2.
Half.
1 by 2, right? Now
Yes,
again, look at this. What is my small n by capital N?
1 by 2.
You see the small n is same, small m by capital N. So you can see that the binomial and hypergeometric are almost the same. When I have the small n the same and this m and by n is equal to 0.5. That's why I wrote this as, I told you that I am writing this as n into m by n. What is the expectation of a binomial random variable?
N into p.
M upon n.
Into p. The variance of a binomial random variable was n into p into 1 minus
1
p.
minus p.
So
Yes,
this m by n, you can see that when that m by n is constant, you can see that the binomial and hypergeometric, okay, that is when it's very large, n is very large and m is also very large when compared to the small n, you can see that the binomial and hypergeometric are almost the same. Can you see that?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay. So you can see that how the binomial and hypergeometric distribution, but here your capital N is also increasing. As long as small n was small, it was the same. But when I increase that small n also, you can see that the distributions are not the same. Even though the shape is the same, the distributions are not the same. Can you see that?
Yes, ma'am.
Okay. Right. I think I'm running out of time. I'll try and do how much I can. Okay. Yeah, the dependency for large capital N and small n also. It depends on all capital N, small n, and small n. Okay. Right. The next thing is very important distribution that arises is what we refer to as the Poisson distribution. Now, many a time we are interested in knowing the number of events that could either happen in an interval of time or interval of space. Now, what do I mean by interval of time? Suppose I'm interested in the number of vehicles passing through a check post in time interval, say 9 o'clock to 10 o'clock. Okay. Or I'm interested in knowing as the number of spelling mistakes in a book. The first time I'm interested in knowing, I'm counting in an interval of time. In the second case, I'm counting the number of events in an interval of space. Agreed? So in this kind, whenever I want to know the distribution of a number in either an interval of time or interval of space, again, remember it is not continuous, even though I'm calling it as an interval of time and interval of space, because I'm counting the number of events. Is this clear?
Yes, ma'am.
Yes, ma'am.
I'm counting the number of events. Okay, for example, suppose a person is observing the number of vehicles that pass through a traffic in this one, and she sees that she is counted for 1,001 minute intervals. She sees that in one, and how many intervals. So you can see that this count adds up to 1,000. Okay, she collects data and she sees that this is the distribution of that data. So what is the distribution or the random variable that captures this kind of a distribution? Okay, so in idea is, suppose I collect data comprising 1,001 minute intervals. Okay, of that 81 minute intervals did not have any vehicles going. 225 1 minute intervals had one vehicle passing through. So this is what was my data. Is that clear?
Yes, ma'am.
And this is how I can plot my data, a bar graph for this data, where these are the counts.
Yes,
This is
ma'am.
the frequency. Is
Yes,
this
ma'am.
clear? Now I would want to know what is the random variable I can use here. Okay. Now what is the mean? Can I compute the mean in this case? How do I compute the mean? Go back to your descriptive statistics course. How did we compute the mean? Given this data, I find out the relative
frequency. Yes.
I can find out what the relative frequency. I can find out what is my mean, which is 2.39. And I can find out the variance is also 2.16. Is this clear?
Yes, ma'am.
From this data. So I would want to know what is the kind of distribution that can be applied here. I would request you all to go through the lectures. Prashant, has the lectures been uploaded on Poisson?
Yes, ma'am. On hypergeometric Poisson has been uploaded on portal.
It has been uploaded?
Yes, ma'am. Yeah. Yeah.
Okay. So in that, I have given you the derivation of the probability mass function. So you can see that the appropriate probability distribution, okay, to model this kind of number of vehicles passing through a traffic intersection in a period of time, or to compute the number of events in a period of this one, is what we refer to as a Poisson distribution. So what is the probability mass function of the Poisson distribution? So for example, this number of vehicles, when I'm counting the number of vehicles, it could take the value 0 or 1 or 2 or 3 or 4, or it could take any value. It could be greater than 6. So this is probability of x taking value 0, 1, 2. It can take any value. It is e to the power of minus lambda, lambda to the power of x by x factorial. This is the probability mass function of the Poisson distribution. For example, if I am interested in knowing what is the probability of misprints, if on an average, I say that there are 2 misprints in a page, okay, and I'm interested in knowing the probability. So that's how we can model it as a Poisson distribution. So you can see that this is my observed and this is modeled as a Poisson distribution, where I'm looking at the probability with lambda equal to 0.26. You can see that the Poisson observed and the model distribution, the PMFs are same. Can you see that? Yeah. So whenever I'm interested in modeling the number of events in a interval of time or on space, I model it as a Poisson distribution. So you can see that the graph for lambda equal to 1, lambda equal to 4, lambda equal to 8, as lambda increases, you can see that as the lambda is small, it is positively skewed, but as lambda increases, the distribution becomes symmetrical. That is something which you need to understand. Now, what is the expected value of a Poisson distribution? The expected value of the Poisson distribution, expectation of x is lambda. Again, you can go through this distribution thing, and the variance is also lambda. Now, why is this important? Whenever I ask you, for example, I tell you that the number, on an average, I find 2 typing mistakes in a page. Okay, I'm interested in knowing in a book of, say, 200 pages, what is the chance of me finding 5 typing mistakes? How would you model this as a binomial Poisson distribution? Is the question clear?
Yes, ma'am.
Yes, ma'am.
What is the chance of finding 5 typing mistakes if there is a chance of finding 2 typing mistakes per page and I have 500 pages in the textbook?
It's clear.
If it is 2 per page in 500 pages, what is the average?
It is lambda.
What is lambda?
2 per page.
2 per page, but I
2
have
per page.
500 pages. I have 500 pages. So what would be
So
my?
it is for 200, 2 into 500.
Okay, 2 per page. So 2 into 500 pages. So what is the chance of me finding 5? So I need to just find my lambda. Once I know my lambda, I plug in that value of lambda. Okay, here, probability x equal to 5. All I need to know is what is lambda, right?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Once I find that lambda, I can plug in that. So whenever you are encountered with problems, which is asking you the number of vehicles passing or number of people withdrawing in an interval of 15 minutes or number of, so for example, again, interval of 15 minutes, suppose I tell you what is the chance of number of, on an average, the 10 people withdraw money in 10 minutes. So I'm asking for an hour. Then afterwards, you know that if it is 10 people in 10 minutes, then afterwards you'll have to extrapolate that for an hour. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yeah, so number of telephone calls received per minute in a call center is known. What is the chance of me getting 100 calls in an hour? These are the questions I ask. You'll have to model it as a Poisson distribution. Is that clear?
Yes,
Yes,
ma'am.
ma'am.
Yeah. So whenever you are asked questions which is asking you to find the number of events that happen either in an interval of time or interval of space, you can model it as a Poisson distribution. Is this clear?
Yes, ma'am.
So this was about the discrete distributions, and we saw the Bernoulli, we saw the binomial, we saw the hypergeometric. The thing that you need to understand about the binomial is Bernoulli has 2 outcomes, success and failure. Binomial is IID, that is independent and identically distributed Bernoulli trials. In hypergeometric, I lose the independence, I lose the identical distribution. Poisson is a way of actually, if you refer to the lectures, we have derived the Poisson probability mass function as an approximation of the binomial distribution. Now, why is it an approximation of the binomial distribution? Now, if you look at number of typos in a book, okay, I can look at number of typos in 10,000 words. 10,000 words or 1 lakh words. So my n is very, very large and my p is very, very small. So this lambda, right, when n is very, very large and p is very, very small, I cannot model it as a binomial distribution. In that case, I might seek a binomial. That's why I'm talking when n is very, very, very large. Instead of looking at it as n discrete events, I can talk about it as an interval of space or interval of time. Does that make sense? Yeah.
Yes.
When n is very, very large, I have say 1 lakh words. Instead of saying how many typing errors are there in 10 words, when I know that the probability of making a mistake is say 0.25 or something, I can find out that probability that among 10 words, 1 is a typing error. But when I have this probability of making an error is very, very less, say 0.05. And I want to know what is the probability of finding a mistake in 10,000 or 1 lakh words. That n choose I is going to be very difficult to compute. Would you agree? So in that cases,
Yes, ma'am.
Poisson seems to be a good approximation to the binomial distribution. Is this clear?
Yes, ma'am.
Okay. So the next thing which we will look at is what is a uniform distribution. Okay. Now in the discrete uniforms case, I said that, okay, I have this as my probability mass function. X was taking the value x1, x2, x3 up to xn. Each one of them had the same probability, right? Now in the continuous uniform space, I have a value, okay? I have an interval and I'm telling that the chance of finding x in this interval is the same. That's what is the same. I don't have a chance of finding x in this interval to be different from here. The chance of finding x anywhere in this interval is the same. That's why I'm saying finding x in an interval. I'm not saying x taking a value. I'm telling x finding in an interval. Is it clear?
Yes, ma'am.
Yeah, ma'am.
Okay. So now if this x is the same, so for example, I want to know what is this value. Okay, so I have this a, I have this b here. This is my f of x here. I know this f of x is constant in this interval a to b. Now, if this is a probability density function, what do I know about this f of x dx? If it is a probability density function, what should this be equal to? The area
1.
after this curve? This should be equal to
1.
1.
Now, I want to know what is the value of f of x. Now, this f of x is a constant. Okay, let me call that constant to be k. K dx a to b. What is the integral of a constant between a to b and k dx? What would this be?
X.
K times x.
K times
K
x.
times x. K times x.
Definite integral a to b. So, what would this be?
Yes,
K.
ma'am.
It would be k into b minus a.
Yes, ma'am.
That is equal to 1. So, what is the value of k?
1 by b minus a.
Okay, so the probability density function is 1 by b minus a for any x that lies between a and b. Is that clear? And it is 0 everywhere else. Is this clear?
Yes, ma'am.
Okay, so this is the uniform distribution. So f of x is taking the value 1 by b minus a for a lying between x and a to a and b. Now, what is the expectation of this random variable? I know what is the probability mass function. Okay, so the expectation of this random variable is again a to b, x into f of x dx. This is from a definition.
Yes, ma'am.
So this would be a to b. What is the value of f of x? It is 1 by b minus a dx. 1 by b minus a is a constant into a to b x dx. So what would this be? What is integral a to b x dx?
X square by 2.
X square by 2. But definite integral, it is going to be b square minus a square by 2.
Yes, ma'am.
Into 1 by b minus a. But what is b square minus a square?
B minus a
into b minus a.
B minus a b plus a.
B
plus a into b minus a.
So my expectation of this random variable would be b plus a by 2. Is that clear?
Yes, ma'am.
Similarly, what would expectation of x square be? X square f of x dx. That would be 1 by b minus a to b x square dx. So what would that be?
X cube by 3.
By 3.
That would be b cube minus a cube by b minus a. Is that right? 3
Yes,
into b minus a. So what would variance of x be? It would be b cube minus a cube into 3 into b minus a minus b plus a whole square by 4. Would you agree? Expectation of x whole square?
Yes, sir. Yes,
Yeah.
ma'am.
Right. Now b cube minus a cube. What is b cube minus a cube? You can check that. You'll get this is b minus a whole square. Sorry, this is b minus a whole square by 12. Is that clear?
Yes, ma'am. Yes, ma'am.
Right. Okay. Now, if you remember, when I looked at the, what was the cumulative distribution function for x is between a to b. So this is my density function, right? A and b, f of x. F of x is, this is 1 by b minus a, right? Would you all agree? This is the value of 1 by b minus a. Is that right?
Yes, ma'am.
Now, suppose I have a c here. What is probability x is less than or equal to c?
0.
C is 0.
0.
At this point, what would it be?
1.
At a. At a.
0.
0.
Ma'am,
0.
0.
0.
For x belonging to a. At here, it is taking the value 1 by b minus a, right? Slightly greater than a. Right? So for
Yes, ma'am.
if c is here, what is the value it will take? It will take the value integral a to c,
Fx.
1 by b minus a
A.
dx. Would you agree?
Yes, ma'am.
Right? What is that value? That would be c minus a by b minus a.
Yes, ma'am.
So for any c which lies between a to b, it would be c minus a by b minus a. Would you agree?
Yes, ma'am.
For c greater than this b, it is going to be 1. Agreed? The cumulative distribution function.
Yes, ma'am.
Right.
Right? Okay. Now, if I have to plot this function over all x and f of x, till it hits a, what is the value of this function?
0.
0.
Beyond b, what is the value of the function?
1.
1.
1. Okay. For any function here, that is for x lies between a and b, would you agree that I can write this x minus a by b minus a in this way? Minus a by b minus a plus 1 by b minus a times x. Can I write it in that way?
Yes, ma'am.
Now, can you recognize this? Minus a by b minus a plus 1 by b minus a into x.
Yes, ma'am.
Straight line.
Straight line, right?
Straight line equation.
This is
Yes, ma'am.
mx by
Mx plus c.
c. So this is a straight line. It is continuous. Agreed?
Yes, ma'am. Yes, ma'am.
So you can see that the CDF of a, so you remember the CDF of your discrete was this way, right? I had a step function with discontinuities.
Yes, ma'am.
Yes, the CDF of this uniform would be in this way. Is this clear? Now this
Yes,
is
ma'am.
continuous.
Yes, ma'am.
It's 0, then it is a straight line, then it will be 1. Is that clear? The slope of that straight, what is the slope of the straight line?
M. B minus
1 by b
1 by
minus
b
1
minus
by
a.
b minus a.
Suppose a is equal to 0 and b equal to 1. What would be the slope of that line?
1.
1.
Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay, so you can see how the slope would change for 1. Okay. 1 second. There is something in the chat box. Let me see that. X is uniform between 2 p.m. and 3 p.m. Okay. X is train departure time. Train might depart from station at 2:30 p.m. But X equal to 12:30 p.m. is equal to 0. Train will depart at 2:30. Okay, let me tell you what, when you are telling this, yeah, that is a question which you ask, but typically when you're asking what is the chance that this train will depart exactly at 12:30 p.m. Is that the question that is being asked?
Yes, ma'am.
Okay. Now, the question is, it is not an impossible event or something. See, the thing is, when you're talking about a continuous random variable, you are not telling about the value this is taking at every discrete point. You're only talking about the value it is taking in an interval. Okay. So instead of telling that probability X is exactly equal to 12:30 p.m., if you say that the probability X is between 12:30 p.m. minus some epsilon to 12:30 p.m. plus some epsilon, that can be found out, but not probability X is equal to 12:30. Does that clear?
Yes, ma'am. Means 12:30 to 12:30 and 30 seconds.
Yeah,
Like that.
plus some epsilon, however small that epsilon is, that I can compute. This is computationally. I'm not saying probability X equal to 12:30 is an impossible event. I'm just saying that the probability 12:30 minus some epsilon to probability 12:30 plus epsilon will capture what you want to do. Is that clear?
So if epsilon tends to 0, the probability will be non-zero.
For very small epsilon, but that is not what. See, what we are trying to do is we are trying to capture the probability that it lies in. See, the distances, you're not asking here exactly what is the probability X is equal to a value. You're just asking all the time probability X belongs to an interval when you're modeling it as a continuous random variable. Is it clear?
Yes, ma'am, that's clear. But you said that we can put an epsilon.
Yeah, so the tending to 0 is so the probability would be 1 minus this, right? So it does not mean that the probability, see, the way you should understand is you always express it as probability X belongs to some interval. That's what I want to tell. Okay. So the tending to 0 would not make any great sense here from an application point of view. Is that clear?
Yes, ma'am. Yes, ma'am.
Okay.
From application, we should take at least 5-second interval or 10 seconds.
So the idea is you're talking about some intervals there. Okay. When you're saying that it can happen at any time interval, that's what you're trying to say. Is it clear? See, for example, let's look at this. Okay. Now, suppose I'm looking at the number of minutes of playing time. Okay. In a randomly chosen curve. Okay. Right, the number of minutes of playing time of a certain basketball player. Now, what does this tell you? How would you, what does this tell you? How would you explain this curve?
Between 10 to 20, there is probability that.
Yeah, there's a 25% chance that this person would play between 10 to 20 minutes or between 30 to 40 minutes, but the chance that they will play between 20 to 30 minutes, it is high, 0.05, yes, right? It's 0.025 and 0.025. Now, is this a probability density function?
Yes, ma'am, it is
Yes, ma'am.
probability density
function. How would you verify that? What is the area under this curve? What is this area? What is this area?
0.25.
What is this area?
0.25.
What is this area?
0.5.
So what is the total area?
1.
It is 1. This is 0.2. This is 0.5. This is 0.25. So the total area is 1. And I have f of x is greater or equal to 0 in this one. Okay. Now I want to know what is the chance that the playing time of this college basket player would be less than or equal to 25 minutes. What is the area?
Find area under 25 minutes up to 25 minutes.
10 to 25.
So this is the area I'm interested in knowing,
Yes, ma'am.
right? This is the area I'm interested in knowing. Is it clear?
Yes, ma'am.
Greater than 25, I can find that out. Okay, right. So you can see that the probability that the person is playing over 20 minutes,
10 to 20.
15 to 20 minutes, I can find out all these areas I can find out,
Yes, ma'am.
right? Which you can see that I just added it up here and you can find out. I think here it should be a 0.05. I think this one. Now let's look at this distribution. It is 2 p.m. now. Okay, and I want to study for statistics till 6 p.m. So what is the total time interval here?
4 hours.
4 hours.
Okay, but now I know that I might have probability and the actual time I would spend is a random variable. So what is the curve I'm plotting here? The time I would spend between 0 to 1 and 1 to 2, 2 to 3, 3 to 4. This looks like a triangular distribution.
Yes, ma'am.
Yes, ma'am.
Okay, so now let's look at it. What is the height of this curve at 2? What is the total area under this curve?
0.5. 1.
What is the total area under this curve?
1
1.
What would be the height of this curve?
must be 1/2.
So what is this?
Half into base
approximation?
into height is equal to 1.
Yeah. So now what would be the what would be the height?
4.
Okay. What is the probability that the person would study for more than 3 hours? If this is half, what is the probability that the person will study for more than 3 hours? You know this base also, right? If this is half, what would this be? This is 0.25,
Yes, ma'am.
right? Now this, what is this? What is this area? What is this area?
0.25.
0.125.
0.125, which is 1/8, right?
Right.
Yes, ma'am.
What is this area now? Probability that she'll study between 1 hour and 3 hours. What is the area of the rectangle? What would this area be?
2 into 0.25.
Yeah.
0.5.
0.625.
What about this?
0.5.
So what would be the total area?
0.75.
Which is 3/4. Is that clear? Yeah. So now let's look at, suppose I am given an A, B, and C. You can see that in this area I have a line. What is the slope of this line? What is the slope of this line? If this is C.
0.5.
No, not for this. Suppose I'm given, instead of 0, this one, I have an A, B, and C. A, C, and B. What is the slope of this line? If this is C minus A, and suppose this is some D. What would this line be?
D by
Suppose I'm giving you this is A1, A2.
D by C minus A.
So this is D by C minus A. Is that right? Yeah.
Now vertical height by
Yeah. What would be the slope of this line?
it will be negative D
It would be
upon
negative, right? So here, this is the case of a symmetric distribution. So I could have a distribution which is like this. I could have a distribution which is like this again, same triangular. So, but what do I need? I need to know what is the minimum. I need to know what is the maximum, and I need to know the point at which I have the highest point. Is that clear?
Yes.
And I can define what is called a triangular distribution. Is this clear?
Yes, ma'am.
Okay, when I have different slopes, I can define what is called a triangular distribution. Now, one of the most common distributions that you encounter when you want to model the inter-arrival distributions or service times or anything is what is called the exponential distribution. What do I mean by inter-arrival distribution? Now, imagine a bank where I have customers arriving into a bank, okay? Or a hospital where I have patients arriving into a hospital. So the time between two patients or the two customers into a bank, is that deterministic or is that random? The time between the arrival of two customers in a bank or the time arrival time between two.
Random.
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 It's random.
So so I want to know what is the distribution. So it could be 1 minute, it could be 5 minutes, it could be 25 minutes, it could be anything, right? So that is what we refer to as an inter-arrival time. Similarly, if you go to a bank, you have a bank officer or a teller who is serving you. Does that person take the same amount of time to all the customers or is it different?
Different.
Different, ma'am.
A doctor who is serving the patients, or consulting with the patients, does the doctor take the same amount of time to every person?
No, ma'am.
It could be different, right? So typically, these are what we refer to as service times. Okay, and one of the distributions to model this inter-arrival times or this service time, one very popular distribution is what we refer to as the exponential distribution. Now, what is the exponential distribution? It has a density function. For some parameter lambda greater than 0, it is lambda e to the power of minus lambda x. Okay, this is said that x is exponentially distributed with parameter lambda. So you can see that this is the distribution or the shape of the PDF for different values of lambda. So what is the CDF? I know probability of x is less than or equal to a, which is 0 to a lambda e to the power of minus lambda x dx. What would be this? Lambda is a constant. So if I remove lambda is a constant, what is this integral?
E to the power minus lambda x.
By lambda, right?
By lambda. Yes, ma'am, by lambda.
And I have a minus also because there's a minus lambda. So this lambda and lambda get cancelled. Yes. So this is between 0 to a. So what is e to the power of minus 0? E to the power of 0?
1.
So this is a 1 minus e to the power of minus lambda a. So this is what is my cumulative distribution function. Okay, so you can see that we plotted the cumulative distribution function for a uniform distribution where I had a straight line, right? Now this is the curve for the cumulative distribution function for a exponential distribution. So you can see that all of them after 1 it is the same. Can you see that? It is less than or equal to 1 and after 1 it is the same.
Yes, yes, ma'am.
This is not a straight line. Is it clear?
Yes, ma'am.
Yeah. Okay. So the expectation of a exponential distribution. Okay. Now again, let's look at the expectation. So what is the expectation of x? X into f of x, lambda e to the power of minus lambda x dx. Okay. Now what would be the expectation of x? You can just show it through integration by parts. I'm not going to do that here. You can check through integration by parts. Expectation of x is 1 by lambda and variance of x is 1 by lambda square. Okay. So how do you use it? Suppose I tell that a person on an average, I know that there are 25 people who arrive on an average to a the 25 people arriving in a particular thing. I can find out what is the average number of people arriving in a bank in a particular day, and from that I know that the mean of the exponential is the reciprocal of the parameter. I can identify what is the parameter of distribution. Okay, once I know this parameter of distribution, I can find out what is the mean and the variance. Okay, that is how I can use the exponential distribution. So in summary, what we have learned today and what I want you all to understand is there are discrete and continuous random variables. Depending on the situation, you will decide whether, so whenever you have a count, it is going to be a, so whenever you have a count, so this is what is the first thing which I did is when I have a discrete and continuous. Discrete is number of people, number of languages, or number of times. When I'm counting, it would be a discrete random variable. Whereas when I'm measuring, be it temperature, height, speed, weight, time taken, it would be a continuous random variable. When I have a discrete random variable, I talk about the probability mass function. When I have a continuous random variable, I talk about the probability density function. For both of them, I know that summation probability x equal to xi should be equal to 1, which is the same as f of x dx equal to 1 over the interval a to b. The area under curve should be equal to 1. I define a cumulative distribution function for any random variable as minus infinity to a f of x dx, which is going to be up to a, or x is less than or equal to a, p of x. This is going to be my f of a here. I know here the cumulative distribution function is discrete and it's a step function, whereas here it is continuous. We saw the cumulative distribution function for a uniform distribution and an exponential distribution. When I talk about discrete distributions, I started with a Bernoulli distribution here. The parameter of Bernoulli distribution was P. The expectation was P. The variance was 1 minus P. I went to a binomial distribution. A binomial distribution is IID Bernoulli trials. The parameters are N and P. The expectation is NP. The variance is NP into 1 minus P. When I lose the independence, I have a hypergeometric distribution. In a hypergeometric distribution, I have capital N, M and N as the parameters of the distribution, where M is of one kind and capital N minus M is of the other kind. N is the sample size. Then we went to a Poisson distribution. In a Poisson distribution, I have a parameter lambda. The mean and variance of a Poisson distribution is lambda. This Poisson distribution is used when I want to model number of events in an interval of space or interval of time. That's about the discrete distributions. In the continuous distribution, we started with a uniform distribution where I have the density, which is uniform in an interval. The uniform distribution, then we saw a non-uniform distribution. When I saw a non-uniform distribution, I saw a general non-uniform distribution and a triangular distribution. And then we looked at an exponential distribution. Exponential distributions are typically used to model inter-arrival times or service times. Here the distribution, the mean is a plus b by 2. In an exponential distribution with parameter lambda, the mean is the reciprocal of the parameter, or the reciprocal is the mean of the 1 by mean, and variance is 1 by lambda square. The most important continuous distribution is the normal distribution. And I think are they introduced to normal distribution in Stat 1, Prashant?
No, ma'am, not yet. We will upload as extra content, but normal distribution will not come in the quizzes.
Okay, normal distribution will not come in the quiz.
Yeah,
right?
but we will upload as extra content so that they can study.
Right. So is there anything else you want me to talk about? Prashant?
No, ma'am. I think everything has been covered.
Has been covered.
Yeah.
So if there's any doubts, I'd be happy to take. We have about 5 minutes left for the session. Any doubts or any clarifications? I'd be happy to handle it.
Ma'am.
Yeah.
We only calculate the area in continuous variable.
Hmm.
We can't find exact probabilities, ma'am.
Yeah, you
I'm
cannot. If it's continuous, you cannot. If it is a continuous random variable, talking about x equal to any xi is not possible. It's only x belonging to a particular interval. That's the area. That's what you are talking about. Okay.
Thank you, ma'am. I'm
Right.
understand that clear.
Yeah. Right. Okay, I should have talked about geometric distribution, but since I did not talk about the geometric distribution, I don't think I will justify the term hypergeometric here. Okay. The weightage of marks of week in end-term examinations. The team should be able to help you with all of this. This is more an administrative question. Okay, Prashant, so I think you can tell them about that.
Yeah.
Okay.
Yeah, we have told earlier as well. So more or less, I mean, approximately more than 65% will cover of week 9 and 12, and the rest of the 35% will be from 1 to 8.
Okay.
Major focus will be 9 to 12 weeks for interim exam.
Yeah. Yes, I think that is the.
What will be the percentages week-wise?
Week-wise is not like that. It's
Means first quiz, second quiz, and last.
What do you mean by quiz? It's a week-wise,
It's
right?
the first quiz, 1 to 4, 4 to 8, and 9 to 12.
Yeah, so first to 4 week you can expect approximately 15 or 20%, and 5 to 8 you can expect 15%, and rest of the 9 to 12 week you can expect 65%. I mean total will be 100%. 65% will be from 9 to 12, and rest 35% will be 1 to 8.
Thank you.
Yeah, thank you.
Yeah, when is the enter?
This Sunday, ma'am, 11th December.
11.
Okay, great. Wish you all the best. Okay. Right.
Thank you, ma'am.
Thank you, ma'am.
Thank you,
Yeah.
ma'am.
Very much.
Thank you, ma'am.
Thank you, ma'am.
Thank you all. Okay.
Yeah, this is actually, ma'am, very, very helpful. We means listen your lecture, but whatever today is clear, very much clear. Thank you very much.
Good. Yeah, you can ask me any more doubts you have. I'll be happy to clear it.
Yeah, but
So this is
still,
you've compressed almost 2 to 3 weeks in this one. Yeah, but I think if you get it at a conceptual level, that is good. Okay.
yeah. Concept is more clear today compared to
Okay, right.
yeah.
Any advice for the end-term exam?
Do well.
Thank you, ma'am.
Okay, do well. Give your best. I think that's the only advice. I usually don't advise people, but that's the only suggestion. You people are old enough to know what to do, so do well. That's it. Okay.
Thank you, ma'am.
Thank you all. All the best. Do well. Okay. Hope you all do this one, finding it useful, and do well. Okay, that's it. Right. Thank you all. So Prashant,
Thank you so very much.
Yeah, thanks. Ma'am.
Thank you very
No,
much.
ma'am.
Thank
Not
you, ma'am.
everything has been covered.
Okay, so I will. This summary, I think these are most of it which have been used in the lectures, but just a summary slide deck. I'll send it to you. You can just share.
Yeah, ma'am, and it's already uploaded on the portal.
Okay, right.
Yeah. Thanks.
Thank you.
Thank you, ma'am. Yeah, thanks.
Thank you all. Good night. Take care. Yeah. Bye.
Yeah,
Good
thanks,
night.
ma'am. Bye. Bye. Thanks, ma'am.
Bye. Bye.
Thank you, ma'am. Good night.
Okay, so thanks, guys. Hope everything has been covered and you got the concepts and all things.
Thank you, sir.
Yes, sir. Thank you.
I think ma'am has covered from week 9 onwards, right? From random
Yeah,
variable expectation. I think All has been covered. Yeah. And you can prefer the tagged live session also from the portal itself, as we have discussed. If you have doubt any topics, you can go. There is a section live session, and in that session, we have uploaded the revision tagged revision live session of the previous term. So if you have any specific doubt, so just go on that time, and there is a YouTube link. You to click, and you will directly go to that topic. Okay.
Okay, sir. And sir,
Okay.
the mock which has been uploaded,
Mhm.
we have it.
Yeah, till 8th December. Yeah.
And sir, the topic that are covered in mock means the weightage like that the same.
Yeah, you can expect you can expect the same. I mean, not exact same as we have discussed. I mean, you can see thing is that you can expect approximately 65% from 65 66 from 9 to 12, and rest of the 35 from 1 to 8. I mean, like you can expect 20% from 5 to 8, 15% from 1 to 4, like that. Okay. So accordingly, you can prepare for your interim exam.
Okay, sir. So 9 to 12 is very important.
Yeah. Okay, then. Thanks. Thank you. Thanks, everyone. Bye.
Thank you.
Nice.
Thank you. Good night, sir.